Hello and welcome. We're going to start talking about rational functions in this video. I was looking at the feedback that you guys gave me in the surveys, and so I'm going to try to take that into consideration with this video, namely that sometimes the learning objectives aren't very clear, so I'm going to put those up front in the beginning, and then also the video length is a little long. So I'll try to figure out a way. Got some ideas on how to make it, try to make it a little bit shorter. So, okay, let's dive in. There we go. All right, so the learning objectives for this lesson are that we're going to figure out first and foremost what a rational function is, and then let's get a red. And then we're going to figure out these notions of holes and vertical asymptotes. What are those for a rational function and how do you find them? And then we're going to look at the end behavior of a rational function. How is it different from the end behavior of a polynomial, which we've been dealing with prior. And then also the horizontal asymptote. And we're going to find that these two, once you find the end behavior, finding the horizontal asymptote is those are the main learning objectives for this lesson. Okay, so let's start off with what is a rational function. So a rational function is a function that is a quotient of two polynomials. So another way to say this is that you can always write a rational function as some polynomial p divided by another polynomial q. So all rational functions are going to look like that. And so since we've got a fraction, you should recall that fractions have problems when you try to divide by 0. For example, 2 divided by 0 is undefined. So for a rational function, we've got fractions, we've got something in the denominator. If we ever plug in a value for x that makes that denominator 0, then our function's undefined. And so the domain of R is determined by the zeros, so the x values that you plug into Q and would make that function 0. So the zeros of Q are going to determine the domain of this rational function. So if you've got some list of those zeros, and I just listed them out, x1 through xn, these are all the zeros of Q in the order from smallest to largest. So like, -2, 1, 3, and so forth, right? If you listed them in that order, then the domain of the rational function is going to be a bunch of subsets of the real line, -infinity to x1, not including, x1 to x2, not including, and x2 to x3, and so forth. And then the one at the end, xn to infinity, is going to be everything bigger than the biggest 0. So, in this case, if we had -2, 1, and 3 as my zeros for Q, my domain would be a bunch of these intervals, -infinity to -2, union -2 to 1, union 1 to 3, union 3 to infinity. Okay. The range of R is a harder thing to find. I would say most of the time for trying to find the range of a rational function, you want to look at the graph of it and figure out, what the highest and lowest values will be. Sometimes you're going to get all numbers, and sometimes you won't. Okay, so looking at the graph would be a good way to determine the range. Okay, so when we've got these undefined x's, these x values that are making the denominator 0, we're going to find that they are going to give us one of two things. They're either going to give us a vertical asymptote, which this slide is going to be about, or they're going to give us a hole, which is what the next slide is going to be about. So vertical asymptote, remember, that's a vertical line. So it looks usually like a vertical line, and you don't draw it in completely, usually dash it. It's where the function will blow up, something like that, as you get closer and closer to that value, to that x value. And so vertical asymptotes are going to be x's that are zeros of the denominator, so zeros of q, but not zeros of the numerator. So any number that makes the denominator 0 but doesn't make the numerator 0 is going to give you a vertical asymptote. For example, x plus 2 over x minus 1 has a vertical asymptote when x equals 1, since 1 is a 0 of q and it's not a 0 of p, right? If you were to try to plug 1 in, r of 1, you're going to find you get 3 over 0, and this is undefined. And so 1 would give you a vertical asymptote. And why is this the case? Why is it a vertical asymptote? Well, let's do a little numerical analysis and figure out what is this function getting close to. What are the values as we plug numbers closer and closer to 1 in? Okay, so I have a little, Desmos app here to highlight what's going on as we plug in numbers that are close to 1, seeing what the output of the function is. There we go. All right, so here's my x plus 2 over x minus 1 function over here, and I plotted some points that are close to 1. So here we're coming in from the left. We have 0.5, 0.75, 0.9, 0.99. So these are getting very, very close to 1, right? As these x's, 0.99 is only 1/100th of a way from 1. And we can see the outputs are getting more and more negative as we get closer and closer to 1. So it's getting very large and negative as we plug in numbers that are smaller than 1. And if we plug in numbers that are greater than 1, so we're starting at 1.5, and then 1.25, and then 1.1, and 1.01. So we're getting closer and closer to 1. From the right, our values, we can see the values are blowing up to positive large numbers. And so the answers of this function are exploding. They're getting huge as you get closer and closer to 1 from either side. So that's why we have this vertical asymptote. And for this particular function, as you were to come in from the left, it's going to negative infinity, and as you're coming in from the right, it's going to positive infinity. But by just looking at the answers of the function, as we get close to 1, we figure out what's happening to our graph. We figure out why there's this vertical asymptote. Okay, so x equals 1 would give us a vertical asymptote. Note, if we tried to plug 1 in directly, see the functions evaluates to undefined. We don't know the answer when x is 1 because it's 3 over 0. Okay, all right. So moving on to holes. Put myself back up here. So a function will have a hole when x equals c if c is a 0 of both the denominator and the numerator, as long as the multiplicity is the same. So for example, we have a function x squared minus 4 over x squared plus 3x plus 2. This will have a hole when x is negative 2, since negative 2 is a 0 of both of those, right? If you were to plug negative 2 in, you would get 4, negative 2 squared minus 4, which is 0. And if you were to plug it into the denominator, you would get negative 2 squared minus 6 plus 2, which is 4 minus 6 plus 2, which is also 0. And so you get this weird 0 over 0, which is kind of also undefined. This is also undefined, but it's undefined in a different way than 3 over 0 was. Because 3 over 0 ended up blowing up, being a very large number, either negative or positive. 0 over 0 ends up not blowing up. It ends up being closer to some value. We'll find out what that value is. So we're going to do, again, a numerical analysis. We're going to plug in numbers that are close to negative 2, which is the thing that we're like, what is the answer? We can't find it. We're going to plug in things close to negative 2 and look at the graph. Oops. Okay, So there's our function, x squared minus 4 over x squared plus 3x plus 2. And I have it evaluated at a bunch of numbers that are close to negative 2. So we have negative 2.5, so this is just to the left. Negative 2.25, negative 2.1, we're getting closer and closer to negative 2 from the left. And negative 1.5, negative 1.75, negative 1.9, these are getting closer and closer to negative 2 from the right. And as we look for these values, we have 3, 3.4, 3.7, 3.97. Note undefined at negative 2, right? It's not an answer there. But the values, as we come in from the left, are getting closer to what looks like 4, right? 3.97 is close to 4. And as we come in from the right, the values are also getting close to 4. 4.03. And so it appears that the function's not blowing up, it's just getting close to 4 as we get close, as x gets close to negative 2. So what we're going to say is that there's a hole at negative 2, 4. So the function has this little point plucked away from it when x is negative 2. And then the value it would approach there is 4. So there's a little point right here on the graph that doesn't exist exactly, okay? And it's undefined there. But it doesn't make a huge impact on the graph. All it is it's a little point that's been plucked away. And that's why we call it a hole, because it's a little hole in the graph, okay? All right, so how do we determine these things algebraically? Because we just did a numerical analysis, we evaluated the function close to those not allowed values, the points not in the domain. So to do this algebraically, it requires us to factor and find these zeros. So we factor the numerator and denominator completely. So using that last example, x squared minus 4 over x squared plus 3x plus 2, we factor the numerator, and that gives us x plus 2, x minus 2. We factor the denominator. That gives us x plus 2, x plus 1. We're going to list out each of those zeros of the denominator. And these will either be wholes or asymptotes. So the zeros of the denominator are negative 1 and negative 2 in this case. You get 1 from each of these factors. And then we cancel common factors with the numerator and the denominator. So what this means is we're simplifying the rational function. So you see there's an x plus 2 factor on top and an x plus 2 factor on bottom. And so once we simplify, we get something that looks like this. X minus 2 over x plus 1. And I'm just keeping track right here for me, and you should do this as well, that there's also that not allowed value of negative 2. Because if we were to not include this, so if we were to write this in here, then there's nothing about that rational function that says you can't plug negative 2 in, but the original one that we started with says you can't. And so to keep track of that information and not lose it, I'm going to write that as part of our domain. Okay? And now we evaluate the simplified rational function at each of those zeros, and if it's still undefined, then the zero is a vertical asymptote. But if it's no longer undefined, then that zero is going to be a hole with that y value. So we're going to evaluate each zero of q. We're going to evaluate negative 1, we're going to evaluate negative 1, and we're going to evaluate negative 2 on this simplified one. Okay? So we're going to plug each of those in. If it's undefined, then it's a vertical asymptote. And if it's equal to some number, then it is a hole at that y value. So we plug negative 1 in. So we'll do the first one. So negative 1 goes in for x. And you're going to end up getting negative 3 on top over 0. That's undefined, and so negative 1 will be a vertical asymptote. So that's the first kind of type. We plug negative 2 in. When we plug negative 2 in, we get negative 2 minus 2, negative 4, and negative 2 plus 1, so we're plugging this one in. So we get negative 2 minus 2 is negative 4, and negative 2 plus 1 is negative 1, and that equals 4. And so this is not undefined. It's going to be a hole, and that's the y value of the hole. So we end up getting a hole when at negative 2, 4, and we get a vertical asymptote when x equals negative 1. And you can see those will both be on the graph, right? You would see that little hole plucked out of the function, and then you would see a big vertical asymptote when x equals negative 1. Okay, so now we're going to move on to talking about end behavior. And a way to think about end behavior is this is like who wins the race. You've got a fraction, and polynomial on top, polynomial on bottom. Both of them are getting big, big, big. But which one's getting bigger faster? It's who wins the race for rational function end behavior. So I've written it out like our general case of polynomials. A n x to the n is our numerator leading term, plus a n minus 1 x to the n minus 1, and so forth, all the way down to a0. Q is a different polynomial, so I'm going to use m instead of n to denote its degree, and I'm going to use b's instead of a's to make those coefficients stick out differently from the coefficients of the top one of p. Okay, so we've got an x to the n plus yada yada yada, and we have bm x to the m plus yada yada yada, and those are our two polynomials. The end behavior is going to be determined entirely by the ratio of those leading terms. So an x to the n over bm x to the m. Okay, so this ratio gives you what the end behavior is. That's all you care about. You can throw away everything else because all of those other terms will be small for very large x values relative to the first terms. Okay, just like polynomials. It's just like polynomials, except now we have two polynomials we're looking at. We're looking at that ratio. So case 1 is that the numerator has a smaller degree than the denominator. So n is less than m. In which case, as x goes either direction, as you go to the left or to the right, then the function is going to approach 0. So the answer will go close to 0 as you get very big inputs or very large negative inputs. So why is this the case? Well, the denominator has a higher degree than the numerator. And so it will grow faster. And what we know about fractions is that, even if you've got, say, 100 on top, if you've got 1,000,000 on bottom, this is going to be close to 0, right? Because you could simplify this down to 1 over, 1,000. And this is very close to 0. And so if the denominator is bigger than the numerator, you're going to get close to 0. So in this case, the denominator is growing faster than the numerator is, and so it's going to go to 0. The denominator wins the race in this case. All right, so here's a little example. We've got x minus 4 over x squared plus 3x plus 2. As we get big with x, as x gets large either direction, then the ratio is going to look like x over x squared. So we're interested in that ratio, leading terms. And if we simplify that, that's just 1 over x. And we know what happens if 1 over x is our function. We go to the right or to the left, that's going to go to 0. Because plug in a large number to that, and you get 1 over a large number, and that's close to 0. So in either case, you're going to get r going to 0 if the numerator is smaller than the denominator. If you're going to the right or you're going to the left. To the right or to the left. It's a mirror for me. So. Okay, so the other case is that they have the same degree. So what happens now if they have the same degree? Well, no one wins the race. They tie, right? And so how do they tie? Well, they tie by going to the ratio of leading coefficients. So whatever the leading coefficients are, that ratio is what you're going to approach, okay? Why? Well, the degrees are the same, and so those x's will balance each other out, and you're going to go to the same value for those, so it's really just those numbers in front of the x's that matter. And so when they tie, you're going to go closer and closer to that ratio of leading coefficients. So again, here's an example. You've got x squared minus 4 over 3x squared plus 3x plus 2, but when we're looking at end behavior, we just care about that ratio there. And so as x gets big, r is going to go towards x squared over 3x squared. And since they have the same number of x's on top and on bottom, that's going to simplify down to 1 over 3. So in either direction, as you go to the left or to the right, it's going to go to 1/3. That will be your end behavior. Okay? And that's our ratio of leading coefficients, 1 on top. And then the third case, so we looked at the degree of the numerator being smaller than the denominator, them having the same degree. And then the third case is where the numerator is bigger than the denominator. What's going to happen? Well, it's going to have polynomial end behavior, just like, we've looked at in the past, determined by the leading coefficient sign, the ratio of leading coefficients sign, an over bm, what's that sign? And then x to the n minus m, is that an even or odd degree polynomial? So, if n minus m is even, it's going to have even end behavior. If n minus m is odd, it's going to have odd end behavior. If the ratio of leading coefficients is negative, it has a negative leading coefficient. If it's positive, it has a positive leading coefficient. And you just default to your polynomial end behavior. So here's an example. So here's negative x cubed minus 4 over x squared plus 3x plus 2. And in this case, when we simplify this down, we have negative x cubed over x squared. And so you have 3 x's on top and 2 x's on bottom. This is going to reduce down to negative x, right? Because we have, we're going to take away 2 x's from the top. And so that's our, negative x is what that goes down to. And so that's the end behavior. It's going to be the same end behavior as negative x, which is an odd degree polynomial with a negative leading coefficient. So that's odd degree polynomial, negative coefficient. Odd, negative, right? Okay? So that's how we look at end behavior for rational functions. And what that leads us to is that there's going to be a value in the first two cases that the function gets closer and closer to as you approach infinity to the left or to the right. And that value it gets closer to is going to give you a horizontal asymptote. So you'll have a horizontal asymptote at that line, or a horizontal asymptote is just a line that the function gets closer and closer to as you approach infinity. So as you go to the right, or as you go to the left, okay? So those will be horizontal asymptotes. In the case of rational functions, you're going to have a horizontal asymptote if that end behavior is approaching some specified number, not infinity or negative infinity. So if the end behavior is approaching 0, or if it's approaching 2 or some other number, then you're going to have a horizontal asymptote at that value, okay? So the horizontal asymptote will be the value the function approaches as x goes to either positive infinity or negative infinity, okay? So let's look at a last example to close this lesson out, down to the bottom corner. Okay, so here's 2x over x minus 1. You can see that the two polynomials have the same degree, and so if we boiled that down, 2x over x, you would get 2 after simplifying. So that's going to be our end behavior. This function will approach 2 as x goes to negative infinity or positive infinity. And so we can see that in the shape of the function in the graph is that it gets closer and closer to 2 as you go to the right or as you go to the left. And here we've got a table set up, 100, I'm approaching positive infinity. We can see the y values are getting closer and closer to 2. And here I'm approaching negative infinity, right? I've got large negative numbers, and my y values are also approaching 2, right? They're just approaching 2 from slightly below. And so that's going to give us this horizontal asymptote where it gets close to 2 but actually never equals 2, okay? And that's all I wanted to talk about in this video. So hopefully that was a good amount of time and not too long. I'm going to aim for under 30, hopefully aim for under 20 if I can, but you know, content-wise and stuff, I can either take the examples out and put them in another video, or you know, what have you. So anyway, we'll talk more about ideas for how to make these videos shorter, but also have the right amount of content in them. Okay, so I will see you guys on Monday, and we'll talk about the survey results then. And yeah, I look forward to discussing it with you guys and improving the class and making it a good class for everybody. So I'll see you then.